Alright everyone, so the concepts you need to remember from Biochem 210 are going to be the four that's outlined on this slide. So we'll look at amino acid chemistry, especially things like the structure, size, charge, and their categories. We'll also look at protein folding, so things like hydrophobic core packing, entropy, etc. We're also going to look at metabolism, where you'll need to know a little bit about how ATP gets hydrolyzed and provides energy for the body, for the cell, and a little bit of basics of organic chemistry, such as SN2 reactions, polar bonds, dipoles, and dipole-dipole forces, and things like that. So let's just dive into them. So in this slide, you're looking at the 20 amino acids that we need to know. But keep in mind that this is not Biochem 210. We're not going to need to know the exact details and specifics of every amino acid. No one's going to ask you the location of the exact atom. So in a way, what we'll need to know is that, number one, every amino acid has a core structure. Okay, so I'm going to draw that core structure right here. So it starts with a carbon, and then it's connected to a hydrogen, and then to a carboxylic group, or carboxylic acid, and then here you have NH3+, which is the amino part. So that's the core structure. If you check them all out, you'll see that all of them have this structure. And what makes them different is the R group, okay? R group, or the side chain. So I'm going to say R is the side chain. Now the categories you see here are only, so we categorize the amino acids only based on their side chains, okay? So if you look at the non-polar amino acids, you'll see that the reason they're non-polar is because of their hydrophobic or non-polar side chains. And same thing goes for polar amino acids, which means that their side chains are polar, and the ones for electrically charged. So it's also useful to keep in mind that, for example, when we say a polar amino acid, such as serine, we don't necessarily mean that the entire amino acid is polar. What we're referring to is their side chain, okay? Otherwise, every single amino acid out of these 20 would be categorized as polar. And the reason has to do with the ends. So if you look at the ends, every one of them has polar ends. So in this slide, I'm going to talk about non-polar amino acids. So non-polar, it means a group or a molecule that is unable to form bonds with water, and therefore it's not soluble in water, and therefore it also gets the name hydrophobic. Now remember the word hydrophobic, where hydro means water and phobic means to fear, so water fearing. They're basically not water friendly. And so the non-polar side chains get their property from having many carbons and carbon-attached hydrogens. Now if you look at the amino acids below, you will see that all of their side chains have carbon-attached hydrogen, or a carbon and hydrogen, or more of the same thing and more of the same thing, and so on and so forth. And these groups are typically uncharged, and they're responsible for hydrophobic interaction. Also, as you'll see in the next slide, there's a difference between carbon-attached hydrogens and nitrogen, or let's say oxygen-attached hydrogens. So we'll touch on that in a bit. If you look at this a little closely, you'll see that there's a little pattern here. And the pattern is that the side chain groups are getting bigger and bigger and bigger, from glycine to, let's say, methionine. And what this means is that the more hydrophobic, so the bigger the side chain you have with carbons, that means the more hydrophobic that amino acid is going to be. And on top of that, if you see a ring, aromatic ring with a bunch of double bonds and carbons, of course that's the property of all aromatic rings, just keep in mind that those are the most hydrophobic ones. And again, we'll come back to that a little later. Before we move on, I wanted to talk a little bit about hydrogen bonding. Okay, so hydrogen bond, it's not a covalent or ionic bond, okay? So if you look at these amino acids here, you can see that the little the lines here are covalent bonds. Hydrogen bond is not that. It's just an intermolecular force. Okay, it's the force that holds molecules together. And there's a huge difference between hydrogens when they're attached to these atoms or carbon. And the difference is that the hydrogen bonding can only happen when H is attached to N, O, or F, either of these three. And I'm going to show that in a second. So imagine we have these free amino acids in our solution, and the solution is mainly made up of water molecules. So that's why I'm going to just draw a few water molecules here. That's one, that's another one, and let's say that's another one. So what happens is, if you have hydrogens that is either oxygen, nitrogen, or fluorine attached, and fluorine is not really important because it doesn't really occur in biological systems, but mainly nitrogen and oxygen, then guess what will happen? So between this water molecule and this alanine, we're going to form a hydrogen bond. And I'm going to show that with little dots in there. So with all those three hydrogens, okay? That's because the hydrogens generally are very positively charged and oxygen is partially negatively charged. So that's why this happens. So I'm going to draw that here as well. But remember that, let's say we have another water molecule right here. Okay. Remember that carbon-attached hydrogens are incapable of hydrogen bonding, okay? So these hydrogens here will never be able to bond with oxygen. So now we'll touch on polar and charged amino acids, okay? So polar in general means, within this context of amino acids, it means water-friendly. It means able to form bonds with water. It means exactly the opposite of nonpolar. And so because it can form bonds with water, it is very soluble in water, which gets the name hydrophilic. So what makes these amino acids polar? Well, polar amino acids get their polarity from highly electronegative atoms such as oxygen, nitrogen, and sometimes sulfur. So if you check these out, the polar amino acids, you'll see, for example, serine has an OH here. Threonine also has an OH plus 1 methyl. Cysteine has an SH. Tyrosine has an OH. Asparagine has oxygen and then amino here. And then glutamine has amino and oxygen. So all of them, almost all of them, have to contain at least one highly electronegative atoms. And by the way, let's take a look at the electronegativity charge that we need to remember for this course. Fluorine, remember, is the first one. Fluorine is the highest, the most electronegative element found known to humanity, let's put it this way. And then after that we have oxygen, and then after that we have nitrogen, and after that, let's say, I'm skipping the other elements because they're not relevant, we have carbon that is almost the same as sulfur, okay, and that is almost the same as hydrogen. But remember, carbon and sulfur, they're very, very similar. They have very similar values, but they're slightly larger than hydrogen. And we also need to keep in mind that charged amino acids, these guys here, acidic and basic guys, are also polar. And the reason is, if you look at the end, even though they're charged, they still contain these highly electronegative atoms. Okay, and so electrically charged amino acids, we have two variations here. We have two categories. We have acidic and basic. And so acidic, of course, the signature of that is a carboxylic group, as we can see here. And basic, the signature of that is an amino group, of course. You can see the same thing in lysine, arginine, and histidine. So having completed the amino acid chemistry, now we can move on to protein folding. Now when it comes to proteins, we're going to look at the hydrophobic core packing, again, how these hydrophobic interactions help proteins fold, and entropy, the importance of entropy in proteins. So hydrophobic effect, what does this mean? It means the tendency of nonpolar or hydrophobic substances to aggregate together and exclude water, okay? And entropy means the degree of disorder or randomness in the universe. Remember, the higher the entropy, the more favorable a process is going to be. And the change of entropy, if you remember the Gibbs equation from physical chemistry, change in entropy is shown with the delta S sign. You will often find that hydrophobic effect and entropy are tightly related in this course because whenever we have the nonpolar substances coming together, they exclude water, and exclusion of water always causes an increase in entropy. So if we look at this picture here, this is a protein. So this is a long protein that we have here. And here we have different bondings outlined. We have disulfide bridge that we're not going to need. We have the ionic bond, the hydrogen bond. What we need to care about is the hydrophobic interactions. Again, so if you can see that from this part of the protein, this is a polypeptide backbone, the green one, we have a lot of hydrophobic groups, and same thing here. So hydrophobic groups, again, have the tendency to find each other and exclude water. That's all you need to know from proteins. So let's look at the exact same topic in DNA. So that's what's going to matter in this course the most. Right off the bat, I want to tell you that I will come back to this slide to explain it in more detail, but I want you to know that in DNA, we have bases that are hydrophobic. So if you can see, this is a single strand of DNA, and these ones are bases, okay? And so this is a zoomed in image of what happens when those bases are solvated by water. So this process here is very unfavorable, meaning that you don't necessarily come across DNA as a single strand in nature. And the reason is this. So if we zoom into this part, so that's like a single base here, let's call that a nonpolar molecule, okay, that's our base. You'll see that we form an iceberg structure. And what that means is that because water is everywhere, the water molecules get themselves very ordered around this nonpolar molecule or around our base. And it's unfavorable because the water is a very polar molecule and it doesn't really want to interact with the nonpolar molecules, right? So what happens is that we add another strand of DNA, so this is another strand of DNA, to make it double-stranded DNA, which is much more favorable. And the reason is, first of all, what's going to happen is that now these bases are facing inwards, so they have the chance to interact with each other and exclude water, right? So we have hydrophobic core packing. And the next thing we have is that we have an increase in entropy. And the reason the entropy increases in this case is because we go from the ordered structure of water molecules to the unordered structure, meaning that there's going to be an increase in randomness. So having covered amino acid chemistry and protein folding, now we can move on to basics of organic chemistry. So in chemistry, a covalent bond is considered nonpolar when bonding atoms have similar or equal electronegativity values. Polar bond, on the other hand, a covalent polar bond, is when the bonding atoms have different electronegativity values. So let's look at it in detail with a molecule of serine. So if I want to draw serine, I'm going to start off by drawing the core structure. And we know that serine has a methyl group here, CH2, and an OH attached to it. So a truly nonpolar bond here is going to be the bond between carbon and this carbon, right? Because they have exactly the same electronegativity values. And also the bond between carbon and hydrogen. Even though their electronegativity values are different, they're not that different for the purpose of this course. So therefore, I'm going to take them as nonpolar as well. However, a good example of a polar bond here would be the bond between this carbon and that oxygen, and this one as well, and same thing with this. What you need to know is that when we have a polar bond, let's say we have a carbon and oxygen bond, let's say single bond like here, what happens is the highly electronegative element, it has the affinity to grab electrons, okay? So when oxygen partially grabs those electrons, what happens is that oxygen gets a partial negative charge, which leaves the carbon with a partial positive charge. Now this is going to be important because you'll see later on that oxygen is typically going to act as a nucleophile, whereas carbon is going to be, most of the time, is going to act as an electrophile. Okay, now let's talk about dipoles. So a dipole, di in this word means two, pole means pole, is a structure with two distinct poles. So we have a positive side of it and the negative side of it. And dipoles are made when molecules have at least one polar bond in them. So if we go back to the previous slide, okay, you'll see that we have this molecule, so this is serine, and we have at least one polar bond in it, right? So this molecule is definitely a dipole, all right? And if you want to investigate a little part of the molecule, which we can totally do, so let's just look at this part of this molecule. So we have the CH2 attached to OH. This is a dipole on its own, okay? This is a dipole where this part is negatively charged and where this part is partially, of course, positively charged. And I can illustrate the same thing with simpler molecules such as water. So let's draw one water here, one water there. So dipole is a property of one molecule, okay? Not a bunch of them. It's not an intermolecular force. It's just a property of one molecule. So if that's one molecule of water, then you'll see that oxygen here is trying to grab onto those electrons. By the way, one single bond is made up of 2 electrons. Again, one single bond is made up of 2 electrons. So it's hard to show it here, but keep in mind that the highly electronegative atoms, such as oxygen, will try to grab onto those electrons and make this side of the molecule partially negative, leaving this side of the molecule partially positive. So now we're going to talk about organic chemistry SN2 reactions and their importance in Biochem 311. So the 2 things we need to know is how to identify nucleophiles and electrophiles. So nucleophiles, that means nucleus loving. So nucleo means nucleus and philes means loving. Nucleus also means positive, right? Because nucleus is positively charged. So positive loving. And positive loving is going to be negatively charged. So that's our nucleophiles. Electrophiles are the exact opposite. So these are electron-loving guys that makes them positively charged. Now, because they carry unlike charges, they always want to bond with each other, okay? And so another definition before I show you a reaction is a leaving group. So leaving group is typically bonded to the electrophile, and it gets kicked out as a result of the reaction. So now let's just take a look at the reaction. So in this compound, we can easily identify the nucleophile, and that's going to be the amino, the amine group. And the reason for that is the nitrogen here is highly electronegative. Okay, so I'm going to put a little negative charge on top of nitrogen right there. In this compound, the electrophile is going to be this carbon in the middle, but not this carbon. And the reason for that is that this carbon is bonded to 2 different electronegative atoms. Okay, so that's going to leave this carbon with a little positive charge. So what happens is that the nucleophile attacks the electrophile, and as a result of this attack, the leaving group is going to be iodine. Okay, so the leaving group is going to grab these electrons and leave. So the resulting 2 products, so the one of them is going to be iodine with a negative charge because it took these electrons from this bond, and the amino substituted compound that I'm going to draw right now. And with respect to Biochem 311, so again, you will not do these Chem 247 reactions in this course. And with respect to Biochem 311, the leaving group is typically going to be the pyrophosphate. You will see this in nucleotide addition cycle when the DNA replicates or when RNA is made as a result of transcription. And nucleophile is going to be something with an oxygen, and the electrophile is going to be typically a phosphate group or the pyrophosphate group. So we're going to finish off Biochem 210 review by analyzing this last slide on nucleotide addition. And the reason I picked this picture and this mechanism of this reaction is because this shows how the polymerase adds a new nucleotide. So in blue we have a nucleotide, okay, to the existing chain, and that's the existing chain of DNA. Now this slide shows that the pyrophosphate is going to act as a leaving group, okay, and we're going to incorporate this base into the existing chain. Now just right off the bat, we have this as a zeta. I don't know what this means. So just put a base there, guys, okay? So we're going to say base. Now let's just say that one is specifically adenine. Okay, so that makes this molecule, this blue molecule, adenosine triphosphate, or our favorite common friend, ATP. So what happens is that the existing chain of DNA acts as a nucleophile. So I'm going to say nucleophile. How do I know that? Well, the oxygen here, the OH group, is highly electronegative, and it wants to make a bond with the electrophile, which is this phosphate. Okay, it doesn't happen to this phosphate or that phosphate, just because attacking this phosphate is more favorable chemistry-wise, and that kicks out 2 phosphate groups as a result. So this oxygen makes a bond with this phosphate, and this bond here that carries 2 electrons, it just goes to the oxygen, okay? It goes to the oxygen and giving this oxygen as a product a negative charge. And on the right, again, we have the resultant product. So let's just look at it again. So as you can see, this oxygen here bonds with this phosphate, okay? And as a result, we incorporate the blue nucleotide into the existing DNA chain. And before I forget, this yellow box here shows the DNA polymerase. So this enzyme DNA polymerase is the one responsible for performing this reaction. And again, don't worry about this concept right now. We're going to learn this much more in detail later on in the course. So for now, we're done with Biochem 210 review, okay? And now we're going to start Biochem 311.